Okay. All right. So today I've been assigned to do the review video for the stoichiometry section, and that was lecture 26. So let's get right into it. Okay. So first off, I put 4 different just things on the screen, and these are kind of just representations of something that we're going to be talking a lot about today. And if you look at them, they all have a similar pattern. They have some things on the left of an arrow, some things to the right of an arrow. They have numbers next to the element sign or to the compound sign. And then the most bottom one has to the right of the elements or compounds element or phase, symbols. All right, so you probably know by now, but all of those are chemical equations. So the important thing to understand about chemical equations is that they have reactants and then products, and then the elements and I guess the reactants and products are all described in their physical state by either an S, L, G, or AQ, and those stand for solid, liquid, gas, and aqueous. So, and for the most part, in their standard temperature, standard condition, that's what you'll put their physical state in. So if hydrogen in its standard condition is a gas, you put a G in parentheses behind the elemental symbol in the chemical equation. And then talking about reactants, on the left side of the arrow, those are considered the reactants of the equation. And in chemical equations, we know that the reactants are the substances that are being consumed. So they will be consumed, and then as a result, will produce products. And products are what we know it's pretty simple, but they're produced in a reaction. So it's pretty face value. It's not too complicated to understand the terminology and I guess idea behind chemical equations. It's just reactants, products, and then we describe the elements or compounds in their physical state at their in their standard condition by either a solid, liquid, gas, or aqueous. Okay. Now, stoichiometry. So let's get into kind of what the actual section is about, stoichiometry. So I put some bullet points here just to understand the really simple form of stoichiometry. And honestly, stoichiometry is really simple. It's logistical, it makes sense. And just if you think about it, for a little bit and long enough, you really will be able to understand the ins and outs of it and like manipulate it in order to get to the answer that the question is seeking. So if we look through the bullet points, stoichiometry ratios, they're basically the numbers in front of the elements or compounds that are a part of the reaction. It is the ratio of reactants and products. And then it's really important to remember that all matter is made up of atoms. So we know that these stoichiometry, the ratios, they represent atoms of the elements or atoms of the compound. And then we also know in reactions, whatever we start with, we also must end with. Matter cannot be created and matter cannot be destroyed. Now, this is really important to remember because as we just talked about, kind of the terminology and the actual way that chemical equations are structured is that there's going to be reactants and there's going to be products. Now, we need to remember that the amount of reactants has to equal the amount of products. Now, that doesn't mean there needs to be the same number of free, moving molecules or elements, but the actual amount of atoms from the beginning of the reaction to the end of the reaction has to stay consistent and equal. And then in order to make both sides of the reaction equal, we add coefficients that make the number of atoms equal. And those coefficients are the theory behind stoichiometry. So that's kind of the overview of stoichiometry ratios. And as you can probably tell, it's pretty basic. All we're doing is just equaling and making sure that things are consistent from the end of the equation, or from the beginning of the equation all the way through the end. Okay, and here's just a little bit more continued, just to make sure that the point's getting hit home and that it's, not some blurry parts that I missed. So in a reaction, the number in front of the element or compound can either be thought of as a number of atoms or that number of moles. So remember how I said everything is made up of atoms? Well, that's true, but atoms are what make up moles. So that number that's in front of the element or compound in our chemical equations, that can either represent that number of atoms for that element or compound, or it could also represent that number of moles for that element or compound. But it's important to remember whatever unit of measurement that you decide to use, whether that be atoms or moles, is that you stick to that. You can't use, atoms for one of the elements and moles for one of the elements. It has to be consistent throughout the equation, or else you'll probably end up with some crazy small or big stoichiometric ratios that would produce insane reactions. So that's important to remember, that you're just consistent throughout the entire problem of either using atoms or moles. So when we look to solve and balance out a chemical equation, it's a pretty simple process, and I've broken it down into 3 steps. So the first step would be write the correct formulas for the reactants and products, including physical state. So you would write all the reactants, put an arrow, and behind each reactant, you would put either a solid, liquid, gas, or aqueous, depending on what it is in standard condition. And then on the right side of the arrow, you would put the products. And again, behind the products, you would put solid, liquid, gas, or aqueous. So this is really important to start with, because if you're not starting with the correct chemical formulas, then in terms of, say, H2O, if you put H3O, but it told you to do water, well, then you're going to have when you go to balance the equation, it's going to be off, and you'll end up getting the wrong result and the wrong chemical equation in the end. So it's important to have the correct formulas of the reactants and products before you even start trying to balance out the chemical equation. Second would be balance one element that appears in only one reactant and product first. So in each equation, and later on, we're going to get into some practice problems and different ways to solve them. But in each equation, we're going to look for a element that appears for the products only in the product once, and then appears in the reactants and only in the reactants once. And we're going to balance that. So we're going to make sure that it has the same number on the product side as it does on the reactant side. And then finally, once you start to kind of balance it out, you're going to choose coefficients to balance all the other elements as needed. And you'll also sometimes come to find that when you finish balancing out the equation, say, you had 2's in front of every single element or compound. You had a 2 before every single product, and you had a 2 before every single reactant. What you're going to do in that situation is, what that just means is basically you maybe didn't see something, or you went above and beyond and had that you can actually divide that whole equation by 2 and then just have 1's in front of every single one of the, has your stoichiometric number in front of each of the products and reactants, as long as, you know, there's a ratio. So if it was like 2, 2, 4, and 6, you can still divide by 2, and then it would cancel out the 2's, and it would be dividing the 4 and the 6. So it'd be like a 2 and a 3 for the 4 and 6, respectively. So that might have been confusing, but like I said, we're going to get into some practice problems just to make that a little bit more tangible and clear in your guys' heads. All right, so here are the practice problems. So I'm going to let you guys kind of take those 3-step plan in order to balance out a chemical equation. I'm going to let you guys take that knowledge I just gave you and kind of look to solve these 4 equations. And then we'll give about 2 minutes about 2 minutes just to solve all of them. And then we'll go over the answers and make sure that everyone's kind of understanding how we got them and, why we got them that way. So I really would urge everyone to go through all 4 of them because it's great practice, and it's the best way to get better at stoichiometry. So yeah, I'll give you 2 minutes. All right. Okay. So let's come back and let's kind of go through the answers and see if it matches up with what you guys got. All right. So here's the answers. So let's kind of go through them one by one and just make sure that it's all making sense and kind of seamless in terms of how we got to the end product. So for the first one, we see that C carbon is only located in one time in the reactants and one time in the products. So that's pretty easy. So and we see 1 to 1. So actually, if I was first to do it, I would just keep it 1. But then we see that there's 2 O2s and there would be 3. So we would have 3 originally and 2 on the reactant side and 3 on the product side. So in order to solve that, by putting a 2 in front of the CO, that's going to produce 2 carbons. So then we're going to have to put also a 2 in front of the carbon dioxide, and that's going to result in two carbons. So now that's balanced. And then on the product side, from the carbon monoxide, we're going to have 2 oxygens. And then from the oxygen gas, we're going to have 2 oxygens. So that's 4. And then 2 times 2 for the reactant side, because you see that subscript 2 behind the carbon dioxide. I mean, that's what dioxide is kind of referring to, that there's 2 atoms, and that's going to result in 2. So there's going to be 4 oxygen atoms on the reactant side and 4 oxygen atoms on the product side. So that's a balanced equation. Now to B. So for potassium nitrate, turning into potassium nitrite and oxygen gas, we're going to look to, it's kind of the same thing. So we see K and N, and only one of them on each side, and then in K and N, again, only one of them on the reactant side. So those are balanced. But if you go to the oxygens, we have 3 on the product side and 4 on the reactant side. Or 3 on the reactant side and 4 on the product side. So we have to have some stoichiometric ratios in order to balance out this equation. So the first thing to do is just try some numbers. So put a 2 in front of the potassium nitrate, and that's going to give us 6 oxygens. So in order to get 6 on the product side, if we put a 2 in front, and we need to put, you could think I could put a 2 in front of the oxygen gas, and then I'll have 4. But now, since we put a 2 in front of the potassium nitrate on the reactant side, we have 2 potassiums and 2 nitrogen. So we have to balance that out on the reactant or on the product side. So that's why we're going to put a 2 in front of the potassium nitrite, and that's going to give us 4 oxygens. That's going to give us 4, and then plus the 2 is 6. So now we have 6 oxygens on the product side and 6 oxygens on the reactant side, and that's going to be a balanced chemical equation. Moving on to C. This one's pretty face value just because we do have one element turning into just another element, and all you want to do is balance it out. So if we have 3 oxygens on the reactant side and 2 oxygens on the product side, the smallest common denominator is going to be 6. So all you have to do is do a ×2 for the reactant side and a ×3 for the product side, and that's going to give us 6 oxygen atoms for both sides. So no matter was created, no matter was destroyed, and that's a balanced chemical equation. Finally, let's move on to D. And first looking at it, on the reactant side, there's 2 nitrogen atoms. So then we're going to go over to the product side, and we see there's 2 nitrogen atoms on the product side. So those are balanced. Then if we go over to the hydrogen, we have 4, but we only have 2 hydrogen on the product side. So we're going to put a stoichiometric ratio of 2 in front of that hydrogen, and that'll give us 4. So now the hydrogen's balanced. Finally, we have 3 oxygens on the product side, and we're going to have 3 on the product side. So we have 3. We have 3 on the reactant side and product side, and reactant side. And 2, and we need to have 3 on the product side. So we have 1 from the N2O, and then we already have a 2 in front of the H2O, and that'll give us 2 plus 1, and that's 3. So that's balanced 2. So if that makes sense, all of those are great examples of how to use stoichiometric ratios to balance out equations to make sure that no matter is created and no matter is destroyed. So let's move on to combustion reactions. Fire. Pretty sweet. Yeah, so combustion reactions, they're a special kind of reaction between some type of fuel and oxygen in order to form carbon dioxide and water. There's 2 types of combustion reactions, just to think about it, and they're complete combustion and incomplete combustion. So in incomplete combustion, we know that some CO or soot is produced, and usually that is derived from the fact that there wasn't enough oxygen when you were burning the fuel, and the lack of oxygen resulted in not being able to produce that CO2 completely. And then obviously this kind of makes sense, but a complete combustion would be that all the carbon is converted into carbon dioxide. So these are interesting because there's always ample amount of oxygen usually in these equations. So it's pretty nice to be able to just use that fuel plus the O2 equals, CO2 and H2O. And we can use that O2 on the reactant side to really manipulate the equation to like it makes it a lot easier, because some of the other equations, if it's not a combustion reaction, you have to go through each one of them and like find the exact stoichiometric ratios. But for combustion reactions, it's quite simple, because you put whatever kind of ratios without having to worry about the oxygen, because in the end you can just produce the correct amount of oxygen just through that oxygen gas on the reactant side. So let's get into some combustion practice. And here's 4 pretty simple fuel and oxygen combustion reactions. And these are all to complete combustion. So we know that all of the carbon is turning into carbon dioxide. So what you're going to do is just go through all of them, balance them out, and make sure that the stoichiometric ratios are to their lowest common denominator. And we'll do about 2 minutes for this one. All right. Hopefully that was enough time to do all the combustion practice problems. But let's move into kind of the answers, and I'll explain why it's that way. Okay. So for the first one, so it's important. So when we look at the fuel type, sometimes it's important to remember that it just like odd numbers or even numbers behind in the actual chemical formula are just important to remember. So for carbon, we have 5 on the right side, or on the left side for the reactants. And we want to get that number on the right side. But you will find that if you were to continue that on, because we only have one oxygen inside of, we have an oxygen in our fuel type, that's going to throw off the actual oxygen in the end, because it'll make it an odd number no matter what. If we only have one oxygen in that fuel, and then whatever stoichiometric number we put in front of our gas, it's still always going to be an odd number. And that's going to make balancing the equation pretty hard. So it's nice to put a 2 in front of that fuel type. So that's going to give us 10 carbons. So then that's going to result in us having to put a 10 in front of our carbon dioxide on the product side. So now we see that our carbons are balanced. So if we move now onto the oxygen, or the hydrogen, for our fuel type, we have a 2 in front of our fuel. So, and that's a 12 as a subscript for hydrogen. So that's going to result in 24 hydrogen atoms. In order to produce an equal amount on the product side, you have to put a 12 in front of the H2O because 12 times 2 is, again, 24. So that's going to be balanced. And now you finally move on to the oxygen. And if you look at, so now it's good to count on the product side. So it's going to be for the carbon dioxide times 10. That's going to be 10 times 2, and that's 20. And then 12, only single atoms of oxygen is going to be 12. So that's going to be 32. And then we see we already have 2 oxygen atoms produced from our fuel type. So all you have to do is put a 15 as a stoichiometric ratio in front of our gas, our oxygen gas, and that's going to be a 15 times 2 is 30 plus 2 is 32. So that's going to be 32 oxygens on the reactant side and 32 oxygens on the product side, making this a balanced equation. Let's move on to the second one. This one's a lot easier because there is no oxygen in the fuel type. So it's pretty face value. All we do is you'll put a 2 in front of the fuel type, and that's going to give us 12 carbons. And then we'll put a 12 in front of the carbon dioxide to give us 12 carbons on both sides. And then we have 12 hydrogen on the product side. So we're going to put a 6 in front of our water molecule, and that's going to give us 12 hydrogen on the product side. Now that's balanced. And then finally, we're going to look at our oxygens, and it's 24 plus 6. That's 30. And then we'll have 30 on the left side. So that's a pretty easy one. The third one, 1 carbon on the product side. So we're going to have 1 carbon on the reactant side, 1, 1. There's 4 hydrogen on the product side. So we have to multiply our H2O by 2 to get 4 hydrogen. So now that's 4 and 4, balanced. Finally, O, we have 2 plus 2 is 4 for the reactant side. And then we're going to multiply our oxygen gas by 2 in order to get 4 atoms of oxygen. And then finally, for our last equation, we see there's a C2. So we're going to multiply that by 2. That'll give us 4 carbon. So we'll put a 4 in front of our carbon dioxide to give us 4 carbon. Now that's balanced. If we move on to our hydrogens, we have a 2 in front of our fuel type. That's going to result in 12 hydrogen atoms. So we have to multiply our H2O molecule by 6 in order to get 12 hydrogen atoms. So now that's balanced. And then if we move on to our fuel type, it's going to be 4 times 2, which is 8, plus 6, that's 14. So we're going to multiply our oxygen gas by 7, and 7 times 2 is 14. So hopefully that all makes sense. If not, just kind of rewind it and listen to that again and try to work through those problems again. And then finally, stoichiometry is a really helpful way to kind of find ratios, mole ratios. And I'll explain what that means in a second. It's kind of hard to understand just in wording, but it makes a lot of sense when you're asked a question. So I'm going to go right through this, and here's some practice. So I'll do 2 of these with you guys, and then I'll leave 2 of you, 2 of them just to kind of do on your own and practice. But for A, it would be how much would 1 mole of CO of carbon monoxide make of carbon dioxide? So this will be interesting. So if we have 1 mole, so if I'm doing my dimensional analysis, I'm going to do 1 mole of carbon monoxide, and then I'm going to do the ratio right next to it. So as we see, every 2 moles of carbon monoxide makes 2 moles of carbon dioxide. So we're going to put 2 moles of carbon dioxide in the numerator. And then we're going to put 2 moles of carbon monoxide in the denominator. And what that's going to do is it's going to cancel out the carbon monoxide, measurement, or, the value. And that's going to give us moles in, our ratio here. So we see that 1 mole of carbon dioxide or carbon monoxide is going to give us 2 moles of CO2. So, and then you're going to divide that by 2, and that will result because you're dividing by the carbon monoxide factor, and that's going to be resulting in 1 mole of carbon dioxide. So 1 mole of carbon monoxide will produce 1 mole of carbon dioxide. Hopefully that makes sense. Now for B, what you're going to do is the same thing. So we have 3 moles. We're going to start with, 3 moles of potassium nitrate. We see, so if we look at the equation, the ratio is for every 2 moles of potassium nitrate, we get 2 moles of potassium nitrite. So it's the same kind of equation. We're going to put a 2/2 ratio. That's what we're going to multiply our 3 moles of potassium nitrate by, because it's 2 moles of potassium nitrite is produced from 2 moles of potassium nitrate. And that's going to result in 3 moles. So 3 moles of potassium nitrate is going to make 3 moles of potassium nitrite. So as you can see, mole ratios are pretty simple. All you do is take the amount they want. So they tell you the 3 moles of one type of compound or element. And then you're going to multiply that by whatever ratio of the numerator of the thing you're wanting to find and the denominator of the moles you already know you have of it. Put that in parentheses, multiply that by, the 3 moles of, or the 1 mole or the 2 moles or the 4 moles or whatever they tell you already have. And that will give you the answer that you're looking for. So that's kind of the end of stoichiometry. Hopefully that was a good clarification and provided some clarity and was able to help you at least have practice problems and give you the time to process it a little bit more and digest the information. And good luck in the test. And I hope everything goes well for finals for you guys. See ya.